Remember long run behavior when we talked about polynomials? For polynomials, we said the long run behavior will look like this, or look like this, or look like this, or maybe the long run behavior will look like this. Long run behavior just means how does the function behave at the ends? Okay, so that's going to involve horizontal asymptotes. And we're going to start by making a comment about long run behavior in general. And long run behavior is going to be a little bit more variable in this section than it was before. Before it only had 4 options. Here we're going to have a few. So it says the long run behavior of rational functions is the same as a long run behavior of, this word shouldn't be here. It's the same as the long run behavior of the ratio of each polynomial's leading terms. Let's break that down with an example later on. If a polynomial's long run behavior is approaching a number, that's a horizontal asymptote, right? We've seen this before. Look at this example maybe not this example. Look at this example, right? The long run behavior is this function's going to 0. The long run behavior to the left is a function's going to 0. That's how we can find horizontal asymptotes. If the long run behavior approaches a number, maybe it approaches 0. Maybe it approaches 2. That's going to be our horizontal asymptote. So long run behavior and horizontal asymptotes are very tightly intertwined, but not exactly the same. Let's clarify this with an example. Let's do this. Find the long run behavior and then, oh my goodness, I just had a very loud Outlook announcement. Find the long run behavior and then find the horizontal asymptotes of these ones. We'll do it by hand and then we'll check on Desmos. So let's use this. This long run behavior is the same as the long run behavior of the ratio of the leading terms. These are our leading terms. Remember, leading terms are only the first ones if they're in standard form. So the leading term is the term with the highest exponent. So what's the ratio of the leading terms? That's 3x squared divided by negative x squared. What does 3x squared over negative x squared look like? Well, as long as x is not equal to 0, these two things, they cancel, right? As long as x is not equal to 0, and x is not equal to 0 here, we care about the end behavior. I don't care about anything in the middle. I want the long run behavior. So as long as x is not equal to 0, these have the same factor of x squared. Oh, so this long run behavior is just negative 3. Okay, long run behavior is negative 3. So as x goes to infinity, we know the y, or the function, let's be consistent. The function is going to negative 3. And in fact, that's true for x going all the way to the right and all the way to the left. We'll just add a plus or minus next to that infinity right here. Ah, okay. And now we can use this piece. If a polynomial's long run behavior is approaching a number, and our polynomial's long run behavior is approaching a number, that's a horizontal asymptote. So that's our horizontal asymptote. Something equals negative 3. Is it x equals negative 3 or y equals negative 3? It's the function value that's approaching negative 3. Also, y equals negative 3 is what horizontal lines look like. Let's get some more practice because these are a little weird. Okay. Part B. Oh, we'll check our answer. Let's check our answer. Let's do it now. 3x squared plus 2x minus 5. Divided by 1 minus x squared. And our claim is that the long run behavior is that this function approaches negative 3. Kind of looks like this y value is approaching negative 3 to me. We graphed y equals -3. We can see that. Oh, look at that beautiful horizontal asymptote. Love it. Love it. Let's do another one. So we know that this long run behavior is going to be the same as the long run behavior of the ratio of its leading terms. Leading term on the top, leading term on the bottom. So what does this simplify to? As long as x is not equal to 0. Because if x is equal to 0, this is 0 over 0, not useful. But for the long run behavior, that's really big x's or really small x's. That's going to be, well, now 2 of those x's, right? This is x times x up here. And the bottom is x times x times x. The 2 of the x's are canceling. So the 2 is still there. Both x's go away in the top. What's the long run behavior of this function? My neighbor is leaf blowing right outside my window. Driving me crazy. I think I've talked about leaf blowers probably. Anyway, so what's the long run behavior of this function? Well, as x goes to positive infinity, as x gets really, really big, what's happening to this? What's 2 divided by a really, really big number? What's 2 divided into really, really many pieces? Going to 0, right? If we divide 2 by a really big number, that's getting really close to 0. So the function going to 0. And similarly, right, if we divide it by a really negative big number, it's still going to be 0. So this is our long run behavior. And there can't be that many. I don't know. Maybe there's a lot of leaves outside. I don't know. If the long run behavior is approaching a number, that's a horizontal asymptote. It's approaching a number. That's good. That's our horizontal asymptote at y equals 0. Ta-da! The answer. Let's check our answer. 2x squared plus 5 over x cubed. Does it look like this long run behavior is that the function goes to 0? I think so. Yeah, looks right. Looks good. Nice. Let's do one last example. Find the vertical and horizontal asymptote. So let's really put it all together. Okay, to find the vertical asymptotes, we look at when is the denominator equal to 0. The denominator equals 0 at these two places. Now, are these both asymptotes or are they wholes? They're wholes if the top is also equal to 0 here with at least as much multiplicity. But there's no factors. They don't share any factors anyway, so we don't have to worry about any wholes. These are our vertical asymptotes. To find the horizontal asymptotes, we need to find the long run behavior. It's not super obvious what the leading term is on these ones. You can FOIL this all out if you want the leading term. But it turns out, that's a bit of a stretch. It turns out that the leading term will also just be what happens when you like multiply all the highest powers of each thing together. But it's a good habit to just multiply it all out if you're uncertain. So the leading term of that numerator will be 4x squared, 2x times 2x. And the leading term of the bottom one is just going to be a regular x squared. So again, as long as x is not equal to 0, because if x is equal to 0, this is not true. But if x is not 0, this is true. For any number that's not 0, this is true. The long run is that this function is approaching 4. Since it's approaching a number, that's going to be our horizontal asymptote. Check our answer with Desmos. 2x minus 1, 2x plus 1. Divided by x, I don't even remember. x minus 2x plus 3. Do we have a horizontal asymptote at 4? Looks like it. Again, it's okay that it crosses. But after it crosses, notice that it's just getting really, really close to 4 again. And do we have a vertical asymptote at x equals 2? Yep, looks like it. What about at x equals negative 3? Yep, looks like it. There we go. We got everything we needed. That's the end of the problem. Now, what does this say? Let's look at this piece. A horizontal asymptote is only if the polynomial's long-run behavior is approaching a number. Oh, and I really should have said if a rational. Gosh, that's a typo that's important. If a rational function's long-run behavior is approaching a number, that gives us our horizontal asymptote. All of these had that the case. So you might be asking, how could the long-run behavior not approach a number? Well, let's look at this example. Okay. What if our function looked like 4x cubed minus 2x plus 1 over 3 minus x squared? So we know the long-run behavior of this is the long-run behavior of the ratio of the leading terms. 4x cubed over negative x squared. And again, as long as x is not equal to 0, this is the same thing as 4x over negative 1. What's the long-run behavior of this? Might be helpful to rewrite this as negative 4x. Oh, the long-run behavior of this is a line called a slant asymptote. We're not going to worry about slant asymptotes in this class. But this says that the long-run behavior is as we go to the right, we approach this negative slope line. As we go to the left, we approach this negative slope line. And again, long run doesn't care about what's happening in the middle. So here our long run behavior is as x goes to all the way to the right, our function's going to negative infinity. That's not a number, the no horizontal asymptote. And as x goes all the way to the left, our function is going to positive infinity. That's not a number, no horizontal asymptote. So if you do see something like this, there won't be a horizontal asymptote. There's what's called a slant asymptote, which we're not going to say. But this would be the slant asymptote, y equals negative 4x. And again, we can see this graphically, 4x cubed minus 2x plus 1. Divided by 3 minus x squared. You actually really can see in this situation. Yeah, this one looks a little bizarre. But let's make the x. Notice that, yeah, we got wild stuff happening in the middle. But eventually the function kind of looks like a line. Eventually the left function kind of looks like a line. And wacky stuff's happening in the middle. So that's an example of when there's no horizontal asymptote. Hope this helps. Let me know if you have any questions, and enjoy rational functions. The end of chapter 4.